In this video, we are going to see how about the electric charge, electric flux, electric field, and also the electric potential. Okay, so we see them one by one. So, electric charge, right? Electric charge, and if you say there may be a plus charge or it can be a minus charge. So that means you have a fundamental charge. Actually, this charge basically when you are rubbing a glass rod with a silk. Okay, when you are rubbing a glass rod with a silk, basically glass rod is a insulator, right? So when you are rubbing with some silk, basically what is happening, there are certain electrons from the glass rod, they have been transferred to the silk. Then what is happening, the silk is acquiring the, or you can say the accepting the electrons, and what is happening, this, if you take a glass that is being giving, so it is being losing the electrons. So that means this glass rod is basically getting a positive charge, and the electrons which is being received the silk, which is being getting a negative charge. So that means this charge is being not neither created nor destroyed, it is being transforming from one to another. Okay, so it is being transforming from one to another. So this is one of the property saying that yes, the glass rod, which is certain properties of the glass rod, it is the total charge remains the constant. Yes, it is transforming from one to another. Okay, and also if you take some another, like if you take a plastic and take a animal fur, in that case when you are rubbing the plastic with the fur, what is happening, basically the plastic is receiving the electrons from the fur, so that there is a kind of, generally when you are doing some rubbing, there is a friction is going to take place, and then due to that the electrons, nothing but the charge is being transformed from to one to another, right? So that means there are certain type of charges already existed and that is being transformed. So you may name it as like, yes, the charge is, the total charge remains the constant. Okay, fine. And yes, coming to the certain applications, I mean certain properties, yes, the charge can be additive property. That means it can be added into one, like charge 1 plus charge 2, like that. Okay, and also you can say that this charge is being quantized and the charge is being conserved. So the quantized charge means the quantization, so you can say that it is the integral multiples of its fundamental charge. Either you may name it as Ne or even Nq. So generally we represent this Q or E is the charge of electron, saying that the charge of electron, that is say 1.6 into 10 power minus 19 say coulombs. Okay, so this is like this. And whether the charge is a vector or a scalar, that means yes, it is having a magnitude, right? And which is a scalar quantity. And coming to, for example, you have the two charges, saying that you have say a plus charge, and you may have, there is one more charge, saying that there is another charge, minus charge. So for each charge it experiences some force. So for example, surrounding this charge, it is experiencing some force of attraction or repulsion. So the region which is surrounded by this experiencing a force of attraction or repulsion is named as the electric field. So it is the region in which where the force of electric force being felt, that is called the electric field. Okay, so this electric fields Generally, you represent them as a vector quantities, and the field lines are basically for a plus charge, the field lines are outwards, and for the minus charge, the field lines are inward. Okay, electric field lines are inward for minus charge, like this, right? And then suppose if you have two charges and these two charges are separated by a distance, yes, obviously there is some force of attraction or repulsion is going to takes place between them. Then that force of attraction or repulsion is explained in the form of the Coulomb's force. So this Coulomb's force, that is F is, F is proportional to the product of their charges and inversely proportional to the square of the distance between them. Okay, so this is called the Coulomb's law. Generally, the Coulomb's force law, you already know the previously, you might be knowing from earlier in the plus one, right? So the like forces, like you have two different bodies, and two different bodies, they have been separated by distance and they have masses, and then the force between them, stating that that is F is proportional to product of their masses and inversely proportional to them, and you have inversely proportional to the square of the distance between them, and yes, that is F is equal to some proportionality constant, and that is m1 m2 by r square. Okay, so the same, but here instead of that masses, we are considered the charges. Now you may know that what is the basic difference between the charge and the masses. Okay, charge and the mass. So basically both are having the magnitudes, both the charges and also the masses, both are having the magnitudes, right? But one thing is very clear, that the mass is must be a positive number. Like for example, you have mass, I mean like so there are different bodies. You may consider that you have earth and moon. Okay, and thus this earth and moon, in between also there is a force is there, that is based on the Newton's principle, right? So you might be represented, that is F is proportional to m1 m2 by r square, say like mass of earth into mass of moon upon its the distance between them, the square of the distance between them, and you have some g value, that is the gravitational constant. Okay, the same we are applying here, but here the thing is, the mass of the earth or the mass of the moon are in the positive number, right? So it may be, it's a kilograms, right? So it may be 1000, 10,000, like, or maybe like you may name it as whatever the mass of that, right? So that is in positive number, whereas the charge can be positive or it can be negative. So this is the basic difference, right? For example, if you take a charge of electron, yes, so you have a positive or negative, you need to find, right? So for a charge of electron is negatively charged, right? For example, if you take a proton, right, so you get a positive charge. So that means that is a basic difference between the charge and the masses. Okay, and this Coulomb's law says like this. Now this F is some proportionality constant, saying that is 1 upon 4 pi epsilon naught into q1, say q2 by r square, because you have the q1 is the one charge and the say q2 is another charge, saying this distance is r. So this may be a plus charge or this may be a minus charge. Okay, so anything you can consider, any combination, plus plus or minus minus. But if you have a like charges, yes, obviously there is a repulsive force between them. You have a unlike charges, there is a attractive force between them. If you have a like charges and unlike charges, now what about your field lines? So here, if you have a field lines are like this, for positive charge the field lines are radially outward, and for a negative charge the field lines are radially inward. Now what about my electric field? In this case, that means you have, so the plus charge and you have the minus charge. Now the field lines are from the positive is being outward. Okay, like this, whereas here is the field lines are going towards to the from the positive towards to the negative. Now like this the field lines, right? That means the negative charge is, the field lines are inward, that means you may name it as radially inward, so into the charge. Here the field lines are outward. Suppose you have two similar charges, if you have plus and plus, now the field lines are just going. So for example, you have plus and you have another plus, now the field lines are like this. That means they are simply away from the, because of the repulsive forces, the field lines, they will not meet. Okay, the field lines will not meet like this. So this is what is going to happen if you have two like charges and separated by distance, and you have the repulsive force between them and the field lines are not meeting. Okay, whereas if you have two unlike charges, the field lines are meeting. Fine. Now, yes, we discussed that the charge is there and the difference between the charge and the mass. Yes, you know the Coulomb's force. Now, what is the expression for the Coulomb? What is the expression for the electric field? So, before that, you may name it as, what is this 1 upon 4 pi epsilon naught means? You may name it as, this is some proportionality constant, that is what you represent, that is K, right? So, this K is 1 by 4 pi epsilon naught. You know the epsilon naught is the value, that is, you may name it as electric constant. Generally, you know that it is the permittivity of a free space, that is 8.854 into 10 power minus 12 farad per meter. Or you can able to calculate knowing the in terms of the, from the formula itself, you know, the force is newtons and this is Coulomb into Coulomb is Coulomb square and this is meter square. So if you want to find out the epsilon naught, the value is 8.854 into 10 power minus 12, and so what you get, you need to find the epsilon naught units, right? So you get, say, Coulomb square upon, say, Newton, or you can write, say, Coulomb square Newton power minus 1 m power minus 2. So these are the units, or generally you write it as farad per meter. Okay, so this is called the permittivity of a free space, or you name it as electric constant. Okay, electric constant. So this is basically the force expression. Now what about the field or electric field intensity? That electric field intensity is F upon Q. F upon Q. That means, like, you know, you may name it as, say that you have two like charges or two unlike charges, whatever, say that their charges are Q1 and Q2, they are equal to Q, but that may be a plus or minus. Now what is happening? Your electric field is being what? 1 upon 4 pi epsilon naught into Q by R square. 1 upon 4 pi epsilon naught into, say, Q by R square. So like this. And one more. Now what about my charge is a scalar? What about my electric field? Does it a scalar or a vector? That makes a matter, right? Right. So yes, we say that we have the charge. Now from the charge, it is experiencing some force, right? So the charge is experiencing some force in the regions. So for that, in order to represent that, you are mentioning the field lines, electric field lines. Now your electric field is what? It is a it is a vector, because it is representing the direction. So wherever the direction is there, you need to say that it is the vector. Not only the magnitude, you have a direction also, right? And this is electric charge and the electric field, and we see the flux and also the electric potential, right? That is very, very important. Okay, so what your flux and the potential says, that makes you very much to understand what my flux is saying, what is meant by flux, and what is the electric potential. So these are the very, very important things you need to understand. Fine. So let's have to discuss about the electric flux. So what is meant by flux? What is meant by a flux? So basically what flux says, flux is represented as phi, and this flux says the amount of, or you can say the number of field lines which are passing through the area. For example, so you have a certain area like this, right? In this area, so somewhere your charge is there. So maybe charge may be somewhere. You can say that the charge which may be in this area. So charge is located. So it can be a single charge or it can be having some system of charges. Okay. So you have like Q1, so Q2 and so on, right? Q1, Q2 and so on, like number of charges. So even though you have a one charge, so for example, if I have a one charge, now say for example my charge is here. So my charge is here, that means from the charge, from that point, I have the field lines which are coming out of the charge if it is a positive charge, or the field lines may be going into the charge if I have a negative charge, right? Very clear. So that means how many number of field lines which are passing in this area, that tells the flux. You are getting my point? So flux is a scalar quantity, yes, which tells the number of field lines which are passing through this area, through this elemental area, whatever you mention. So that makes you to very clear saying that this phi is integral E dot dA. It may be say surface integral. Okay. So integral E dot dA. So E is a electric field vector and this dA is a vector. Now two vectors made a dot product. Two vectors made a dot product, or you say the scalar product, the result is a scalar. So what is your flux? The flux is a scalar or a vector now? It's a scalar, right? Okay, so flux is a scalar quantity. And yes, you can say that from this, you can represent say E into dA because it is E dot dA, so cos theta. So that means your theta and how they makes, because area vector and the electric field, this area vector is generally perpendicular to this area. Okay, now the field lines are also passing, because for example, it is generally we mentioned the area is like this, that means the field lines are either outward of this area or inward of this area. That means if the field lines are just like outward, means it will be like this, or inward means it may be outward or it can be inward into the area. Now what about your area vector? Area vector is also perpendicular to this one. That means that is also just like this one only. Just like this one means it is perpendicular like this, perpendicular to the area. Now electric field lines are also like this only. That means this electric field lines and your area vector, so if both are parallel, then the theta is how much? 0. Theta is 0. Then if the theta is 0, that means you have the maximum amount of flux, or you can say you have the more number of electric field lines which are there. More number of electric field lines are here itself. Now you have this, it may be having some angle. So now the field lines are there. Now the field lines are making an angle with the area vector. That means the theta is not equal to 0. But there is some area is there. That means some angle is there. So for example, if the theta is 60 degrees, then you have a figure, right? So cos 60 is half. That means your flux becomes half of the previous case. Previous means here you get the maximum flux and here you get half times of the previous, the initial one. Now suppose your theta is say 90 degrees between the area and the electric field. Now what is happening? Okay, what's happening? Your flux becomes how much? 0, right? That means the field lines are not coming out or into this area. That means they are perpendicular to the area vector. That means I make you very, very simple. For example, say this is my area. Okay. So this is my area. Now if this is my area, I have taken, so for this area vector is normal to this, right? So area vector is normal means like this. So normal to this one is area vector. Now if the charge is there inside this, now the field lines are coming out, or if the minus charge is there, the field lines are going in. Now what is happening? The field lines are going in or the field lines are coming out. They are parallel or anti-parallel. You may say it is 0 or it may be 180. Now both the cases, what you get? You get the flux, right? You get the flux. That flux is maxima. Now it may be having some angle. So this is my area vector and your angle is making, your flux, your electric field is making some angle from the area vector. Now saying that that may be 60 degrees. Now in that case your flux becomes half of that. Now the last case is, this is your area vector, it won't change. Area vector is like this, your electric field lines are like this. That means electric field lines are like this and area vector is upward. So this makes the flux becomes 0. That means you may name it as in other way, just like the electric field lines are going from one side and coming out from another side. Field lines are coming inside and the field lines are going in this side. Then what is happening? So your area vector and the field lines, electric field, they are perpendicular. So cos 90 becomes 0. So the flux is being 0. Very simple, right? Okay, so this is the beauty behind the flux. So yes, your flux is a scalar quantity, but what is telling? It is telling that the number of field lines which are passing through that. Now, number of field lines which are passing means for what purpose the number of field lines are passing there? Can you tell me for what purpose the number of field lines are passing? Why the field lines are passing or why the field lines are there itself? That means the charge is there, right? Yes, the charge is there in that. That means the flux tells the amount of total charge which is there, which is inside of it. Is it not? That is what the Gauss law, right? So what the Gauss law says? The Gauss law says that the flux coming out of a closed surface is nothing but 1 upon epsilon naught times of the charge inside the one which is enclosed area, whatever you take. Okay. That means the Gauss law says the flux is a measure of amount of charge which is there inside. So that this phi, this electric flux, this is how much? Say Q enclosed, this is enclosed charge upon its epsilon naught times. So 1 upon epsilon naught times of the charge which is enclosed in this. So that is what the Gauss law. Okay, so it's the flux tells the everything. Okay, now this is of course the application of the Gauss law, and in detail about the Gauss law we'll discuss in the next class. Okay, and now, so yes, we discuss the flux and we see the one more one, that is electric potential. Electric potential. Okay, fine. So electric potential. So what is meant by electric potential? What is meant by potential? Generally we used to say that for many things, in our daily language also, we used to use the word of potential. So it tells some caliber, some capacity, some power, some work, some energy for purpose of we are used for potential. So yes, I have that much potential to do this task. That means you have that much, your ability to do that certain task, right? That means for a person, you are able to do that task, you have You have being potential for that, is it not? Similarly, for a charge, for electrostatics, even the charge is experiencing some charge is, there is a exert some force on the another charge, so it experiences some force. It is being felt the certain force, right? So at what distance this process is doing, that is basically we use to find it. Saying that the electric potential, it says, saying you have a charge, say that this may be a test charge, this may be the fundamental charge, and you need to find the potential at this point. Okay, you need to find the potential at this point, saying this point is P. So if you want to find the potential at this point due to this charge, so now you can say that this is the point charge, or you may name it as a test charge. Okay, it's a point or it is a test charge, whatever you say. Now electric potential tells that the amount of work done to bring the charge which is from infinity to that point, because you are going to find the electric potential at this point. That means what you are doing, there is some amount of work has to be done to bring this charge from infinity to this point. So that is what the electric potential. So it is the electric potential is amount of work done to bring the charge from infinity to amount of work done to bring the charge from infinity to this point. Okay, amount of work done to bring the charge from infinity to this point. So that is per unit charge. So that means V is W by Q. So work upon its unit charge. That gives the what? Electric potential. So now I tell you very simple way of finding. Yes, if I don't have this charge, can I able to find a potential here? If I don't have this charge, can I able to find a potential here? No, right? It is not possible. Without knowing the fundamental charge, you cannot find the potential. That means you need to bring some charge to this point. That means for that there is a fundamental charge should be there. Then only you need to go to the infinity to bring it to this point. Without this one, it is not possible. I simply tell you, saying that you have a teacher in the classroom, right? So the teacher in the classroom, saying that he may be the fundamental. So the the fundamental charge is the teacher, and the test charge may be the student. So this student, maybe he may not be attentive in the class. Now what the teacher can do? The teacher can motivate the student to bring him from unmotivation point to the motivation point, right? Right. That means the classroom environment makes the student to the learning point. So from unlearning point to the learning point, it may not be an infinity. It can be any point from that point to this point. Saying that the point it may be A and this point it may be B. Now from point A to B, you need to bring. Then for that you need to do a work on a charge. How much work should be done on this charge? So that makes you to tell the electric potential. Okay, from infinity to this point. So it is very simple. So that means if the teacher is there and he is able to tell you effectively, that means you will be attentive, right? You will be attentive to the classes. So that means what it says, yes, my teacher is well, he is explaining well, everything is fine, I am able to understand. So you came from not knowing point or in inactive point position to the active position, is it not? So saying that your teacher is able to make you to bring to that point to this point, okay, where you are feeling comfortable for your knowledge, is it not? So the same one is going to do this one. So this is it may be having some distance. So you need to find the electric potential for a point charges, or you can able to find the potential for a system of charges. Now whether my potential is a scalar or a vector now? Yes, whether a potential is a scalar or vector, because it is amount of work done to bring from there to hit this, right? So that means it is the scalar quantity. Electric potential is a scalar quantity, flux is a scalar quantity, field is a vector quantity, charge is a scalar quantity, right? So yes, how can I write now? This V is 1 upon 4 pi epsilon naught into say Q by R. So this is what the expression. This is what the expression for the electric potential. Okay, basically this may be extended further, saying that this may be say VA, it may be saying that the potential difference, right? Potential difference, say VB minus VA, that is Q times of its W, something like that. Okay, so that means potential difference. So the difference between these two, it may be a point of say A to B. Okay, so you need to do it in reverse way, VB minus VA. So this is what the potential difference. So in generally what we have seen, that means the concept behind in this class is, yes, you have the potential and also the flux. Without the flux means, if there is no flux means the field lines and the charges, they are being the area vector and the electric field lines, they are perpendicular to each other. That means your charge may be in the area, or your charge is here but the field lines are like this. Or in the other way you can say that, yes, my charge is outside of this area. Now the field which is passing through the area and the area vector, they have been perpendicular to each other. Yes, in that case you may say that very simply, yes, the flux is 0, right? Okay, so this is what the whole idea or the things to be known you guys for a competitive level need to understand for different examinations, right? Okay students, thank you very much, and share this video to your friends for more number of things, because many students will be getting beneficial out of this. Thank you very much.